So this Monday, and then another slot for Monday as well. If you see over here, the schedule, I just summarize the schedule over here because there's no slot over here, so I just skip it from noon 30 to 4 p.m. So please mind that. And on Tuesday, these are the online slots. The offline slots for Tuesday is going to be happening at 5 p.m. You will meet with the AI Singapore. So yeah, the Scramble and general on AI. Please be present here. And on Wednesday and Thursday, a mandatory session with the SME DataX team. These will be all online. All right. So it's mandatory. Please show up. Okay. And right now, it's time for another workshop sessions. The track number 1 is required to join this. Do we need a laptop?
No.
No. Okay. So it will be a very interactive session with you and the speakers. So please welcome Kun Pakhapoom Sarapat and Kun Nut Chukamphaeng from DataX.
Thank you everyone. Thank you for the kind introduction of us. Oh, sorry.
So let us swing the screen for a bit.
Thank you. All right. Okay. Hi everyone. I bet you're having a good time here. I don't want to ruin your mood today, but all I want is just throw some ideas on the floor. And if any of this interests you, please feel free to come talk to us later on in the session. And in this session, the main topic that we're gonna discuss today is how to train, how to fine-tune a large language model efficiently. Okay. By the way, my name is Pakhapoom Sarapat, or you can call me Ui or Poom for short, doesn't matter. I'm an AI scientist at SCB DataX.
And hi, my name is Nut. Yeah, so I am AI scientist at SCB DataX.
Okay, thank you. In this talk, Kunat and I will be presenting two main things, which are the two things here. We believe that these are going to be the must-have ingredient for fine-tuning an LLM efficiently. Those two things are dataset and fine-tuning technique. Okay, and please be ready at the end of the session if you may have any questions. Before that, I think.
Yeah, wait.
Sorry.
No, you can go next slide. Yeah, I think to make everyone know what is the DataX first, I think Kun Ui, can you explain a little bit more about the DataX, what they are doing?
Yeah, maybe you may not realize today, but I think SCB DataX is just maybe is all you need. Because let me tell a little bit about us. SCB DataX. DataX is a subsidiary of the SCBS FinTech Group, as you may know. We specialize in data and AI products. Our main objective is to support other subsidiary business by enabling the power of data and AI to their adoptions, to their implement in their business. Yeah, and we may provide several areas of expertise. For example, we provide the technology, we provide the tools for end user, and we provide the insights on top of the data platform that we have. Yeah.
Yeah, cool. I think everyone here already get a little bit know more about the SAP DataX, and I think we're ready to jump into the detail.
Yeah, but the fact that we also interested in research as well, and our current research topic is the generative AI, especially the large language models. And thanks to 10x it's very honored to be here today as well. Yeah. So before this session, moving forward, I would like to ask you, do you believe that the state-of-the-art performance always achieved by the large data set? Yeah. What if there is another way? Yeah, I will tell you something here. Before that, I would like to refer to the traditional fine-tuning approach or framework, which start from the transfer learning, if you may know about it. So the transfer learning basically contains three main phases, namely the pre-train, the fine-tune, and the inference. So what's going on here? We try to create a generic model first as by using the large data set here in this position, the data here. This is supposed to be large enough, to train so that the model can learn the core knowledge to a certain task, which is in general purpose. And once we have that model, we're gonna fine tune it. Let me give you an example about this one. For example, I'm not sure if anyone interested in playing board game, and there are so many rules for different board games. Even just a certain game, you're gonna have lots of components or whatever. If you would like to build a chatbot for clarifying things about a particular board game, we're gonna create this one, right? But the fact that the model cannot understand the language or the structure of the model, so the training here is to adopt or to borrow the model that learn from the more generic purpose first. For example, the language understanding model to understand the grammar, the syntax, the relationship between words first from the model here. Usually it's called the pre-trained model here, over here. What we need to do further is to prepare the data set which is specific to our use case. For example, in our example, it's going to be the board game rule references. So it means that I have to provide this data set here so that feed into the fine-tuning process and to get the final model here. And once everything ready, we can utilize those models. The model here, usually called as the fine-tune model, And when we have a new inquiry, we just feed it into the model here and to get the output as expected. And in this talk, we're gonna focus on the area here, the fine-tune area, where the magic happens, where we're gonna cook for the model for a specific use case. And the fact that we have an issue here because traditionally we believe that this data set in the fine-tuning process is supposed to be large enough so that it can overcome or make some change to the model that have been trained from the massive data set here. This seems valid, right? But this is way true. Some researcher proposed an idea that maybe the quantity is not necessary because less is more. I will refer to this finding as the Lima, L-I-M-A, which is not the name of city, but it's the model name. So the researchers claim that all of the knowledge, mostly of the knowledge is acquired during the pre-training process. What is left to do is just do some alignment or the fine-tune a little bit to add or remove some features from the pre-trained model to get the desirable outcome. That's the process of fine-tuning. So they test the idea here by using just 1,000 record here, this one here, just in the training set to fine tune a little bit further. Meaning that to train the pre-trained model a little bit using these 1,000 records. It means that these are the results here on the bottom right panel here. We can see some kind of bar charts for the two bar charts here. The first one with the label human, it means that we can use the annotator as, we're going to use human as annotator to judge the performance of the model, which is the comparison between the response obtained from the Lima model from this process and from other models, namely Avatar, DaVinci, BART, Claude, and GPT-4. So it means that if the judge or the evaluator prefer the response of the Lima first, it's going to represent as the Lima wins with the darkest blue here. And if the annotator cannot classify or discriminate between these two responses, it's going to be tied here. Otherwise, it's going to be Lima lose, something like this. What I would like to point out to you here is, let me compare just for the GPT-4 because we all know that GPT-4 is the best right now, right? We can see that it can steal some share from the preference of the user up to, for example, here, 33 if we combine these two portions together. Because if we cannot classify or determine the preference over the Lima response and the GPT-4, it means that Lima is doing great, right? So it means that we can combine these two numbers together, and we can see that this one can gain the share up to 33% as the human evaluator. In terms of the GPT-4 as a judge, we can see that this can gain the share up to what's the number? 34%, right? Yeah. So as you can see here, the technique is not that bad. It's the idea that revolutionized the belief that we have so far about the large data set for the alignment, for example, here. But I wish that the researcher could provide a comparison between the pre-trained that they're using together with the Lima as well to get the stronger evidence or stronger argument to prove the claim that, okay, it relies on just a small data set. But the point that we would like to point out again here is just these 1,000 records here, they manually curate the data set here with their bare eyes. So it means that these manual process cannot be scaled out somehow here. Oops, sorry, I missed the script here. This is just some examples of the Lima response. This consists of 3 columns here, which is the in distribution. It means that we're going to test the performance of the model by using similar query to what we train in the training set. And the out of distribution is like we're going to use a very different kind of query to test the performance and see if it's robust or not. It means that if it can handle another variation of the query or not. And for this one, it's like, because the safety becomes an issue when we talk about the generative AI, because we don't know the generated content is safe or not. So we're going to propose as well. As you can see here, so far, so good, right? Because everything seems fine so far. And the researchers conduct some experiment to answer why less is more. Let me tell you this one by focus on the top left panel here, the top one. We're going to have 3 different data sets, WikiHow, unfiltered one, and filtered one. And I would like to consider just 2 bars first, the WikiHow and the filtered one here. WikiHow represents the data set like the how-to fashion, how to become a YouTuber, for example. And the filter stack exchange contains a variety of the questions. What I'm trying to say is that the effect of the diversity can impact the quality of the model. Sorry, quality of the data set. It means that if the data set that we prepare in the fine-tuning process contains a wide range of the content, we have the high diversity, it tends to provide the better performance when the fine-tuning process done. Yeah, and apart from that, we're gonna compare between the filtered one and the unfiltered one. You can see that the bar chart here for the unfiltered one is a bit lower than the filter one. It basically, the filter one is just, we have the quality filtering method to filter some kind of like some cream from the data set. Unlike to the unfiltered one, it's just everything we just gather around here. And we can see that the quality itself becomes more important when we create a high quality data set. In terms of the quantity as well, they investigate the possibility if we increase the size of the data set that we have. For example, so far we have been using the data set with just 1,000 records. If we increase that number of records to, for example, double it to 2K, 4K, 8K, 16K, up to 32K, what will happen with the data set, with the quality of the data set? As you can see here, it's kind of like it's the horizontal line is stabilized at a certain value. It means that maybe, just maybe, the quantity doesn't that important anymore. I'm not sure. I think, I'm sorry, these are the conclusions of the Lima paper. Yeah, but the question that I just popped out in my mind is that how can we scale the Lima into production or into any other inference? For example, because what Lima did is just manually curate the data set to get the high quality data set, which is painful, right? If you have an experience to prepare the data set, it's going to be totally a mess. I can assure you. So what if we have an automated process to curate or to make the high quality data set? Isn't it good? Yeah, so the idea here from the instruct mining, they propose that if we freeze everything in the setup and just change the data set as the input, so it means that the loss or the loss that obtained from the fine-tuning process can be somehow implied to the quality of the data set. So it means that we're gonna create some kind of like collect some candidate data sets here, and we have some kind of the sampling technique to prepare the data set to get the equally size or to get the equal size of the data set here, different size here. And this data set, we're gonna kind of like quantify its quality somehow by using, it's called indicators, which is the instruct mining rule. Basically, it means that we're gonna try to model it by using the features here, have like some kind of measurement of the qualities as the input, as a feature in the model, and the loss is gonna use as the target of this model, and then try to model it, develop a model to predict the loss from the feature here. Once we have this rule, this model here, we can use to rate the data set for the new one. For example, we have this new data set here. We just calculate the indicator. For example, we're gonna calculate the perplexity, the reward score, or somehow whatever we calculate here, and then feed it into the model here to get the expected loss from the fine-tuning process. And once we have that, we can kind of like set some threshold to define if that data set is a high quality data set or not. Yeah. And this is some result. As you can see here, the red line represents the selected data set, the loss from selected data set, while the blue one represents the randomly selected data set. It shows you that if we consider only the small size of the data set here, we can see that the red one hit the lower point rather than the blue one here. But this difference becomes closer Once the data size increase, for example, to 50,000, so it means that size always beats everything. But the fact that if we don't have that resource that much to fine tune or to train all that huge data set, maybe we can consider just a little chunk of high quality data set instead. Here, that one. As Lima showed, 1,000 records should be enough. And here is kind of like some comparison in the similar fashion by comparing the result from the selected self-instruct process here compared to other, and see if it, but the order may be different. The tie first, lose, and win with the darkest, what is called this? The green blue one color. Yeah, as you can see here, we may compare with the random selection here. The difference between win and lose here is just, the difference is around 10%. Yeah, and for the bottom right panel here, it's just what I would like to show you is just the capability in different angles. So we start from Llama 2, 7 billion, yeah, which is have the skill set here. And once we fine tune with the data set obtained from the instruct mining process to select the high quality data set, we're going to have this blue curve here. The GPT 3.5 is just put here as a reference that, okay, we have the benchmark here. But what I'm trying to say is just, okay, we just compare the blue and the red one should be enough in this case. That, okay, fine tuning with these data set improve the capability in all perspectives. Just summarize what happened so far is that, okay, capability of the models here is mostly derived during the pre-training process. What it did in the finding process is just do some alignment with the specific use case. And the process to, this is just a suggestion, the process to curate or to make the high quality data set maybe calculated from this formula. You may go through the paper for the original equation, but here there's a lot of technical terms here, but the fact that we can quantify somehow, yeah. And at this point, we have the high quality data set. What are we gonna do with this high quality data set? Kunat will show us how to deal with it. Please, Kunat.
Okay, thank you, Kudoi. Okay, yeah, I think, yeah, you guys already have seen that the data quality is most important than the quality, right? And so far, to the second ingredient to train the LLM efficiently, right, is efficient fine tuning. So we still, okay, from the result, why we need efficient fine tuning first. So if you know that, okay, the larger model tend to have a better performance in any prompting technique. So you use the zero shot or you use the one shot, few shot learning. Okay, the y-axis is the accuracy, and the x-axis is the number of examples you put into the context. Okay, if you look at, okay, focus on the different color line. So the blue one, the largest parameter in this graph, tend to have a better performance in any case. So, but to train the larger model, it requires memory in the GPU, right? For example, if you train like a 50 billion parameter model, you maybe need 800 GPU RAM, something like that. So that crazy, right? So we need to find another way to, okay, make it more possible for us. Let's say we just have maybe 40 gig of VRAM or something like that. Okay, how we fine tune it more efficient? Okay, so in this one is LoRa technique. Okay, LoRa technique basically instead of we train the, okay, let's say this is the weight of the model, right? You train all the weight in the pre-trained model and fine-tune it into specific target that you want. For example, you want to do sentiment analysis, classification, you train all of this pre-trained weight, right? But it's not efficient because you have to load this memory into the GPU, right? And also it requires additional memory for the optimizer as well. So instead, the LoLa technique, we can keep, sorry, we can keep the pre-trained weight freeze. We do not load to the optimizer, but we still need to load to the GPU anyway, but not, yeah. But we introduced the metric we call the maybe LoLa adapter. So it's the low length metric. It means it has low dimension and it requires small parameter to train. For example, in this table here, the first one is the, okay, we try to inference each model, each technique. Okay, we have a different technique to fine tune the model, but for the we have a technique called the adapter. This technique, when we fine tune the model, the result here is the inference time. Okay, for 30, for example, 32 batch size. This is the time that to inference this data in millisecond. Okay, so if you use adapter, you may add some additional latency into the inference time. For example, it increased to 2% compared to the full fine tuning, because full fine tuning, you didn't introduce any weight into the model, but for the LoLa, they have the technique to no additional time for inference. And the bottom one, this is the comparative GPT-3 in different fine-tuning technique. Okay, in this one, FT means full fine-tuning. So we take like 175 billion parameter to fine-tune the model, right? And then we get the result here. So we try this one show different technique. Okay, but if you look at the LoLa technique, it requires just small number of parameters for million, and we can achieve the same similar performance compared to the full fine tuning. Okay, but yeah, so but this is not enough because it still requires some space in your GPU card, but can we do it better? So this one we can use what is called quantization technique. So basically the quantization technique is instead of you represent the weight of the model, right? Maybe in the data type of float of 32 or something like that. They use a lot of memory, right? We can quantize it or transform it into small required memory. For example, you can transform the weight of the model from 14.32 into the in 8, something like that. With this formula, basically, how we calculate it. For example, this one 127, right? And then we have x absolute max means the maximum in the input, the weight. For example, if we have the weight set of weight, something like that, right? And then the absolute max means that the value in this weight. And then we do the calculation based on that. And also we can convert back from the quantized data type to back to the original by the process called dequant. So with this, we can save a lot of the memory required in the model by June. So this is the result. Cora, you can call it Corolla or Q-Rolla. This technique, yeah, is a combination between the quantization and LoRa. Okay, so but I will not cover all of the detail, but to give you a little bit of the idea is, yeah, they apply the quantization technique, but in more advanced way, like double quantization, and they have what's called
Sorry, normal float.
yeah, normal float. Yeah. Yeah, you can look at the detail, and don't worry if you are using hacking face or something like that, you can import this technique and apply to your work. Okay, so let's get back to the detail here. Okay, this I will talk with this first. So the rollout means some metric to measure the performance of the model, and the higher is better. And the y-axis means we apply the Q-Rolla into Q-Rolla, or means we apply the Q-Rolla technique to all weight in the neural network. But Q-Rolla FFN means we apply Q-Rolla to only feed-forward neural network in the architecture and for the attention. Yeah, and this means they fine tune without Q-Rolla in the 16-bit, something like that. So, but the thing is, I want to show that okay, you fine tune the model using any method, you get this performance, right? But you use technique Corolla, you can achieve quite the same performance. And okay, so this they compare different type of the data type that they convert quantize to. For example, the info float for and float for the double quantization, something like that. And yeah, this is the mean perplexity, so the lower is better. And yeah, that one the MMLU benchmark. So if you look at it, it's quite similar. Okay, and here is the result that they okay, they have the metric called ELO. So it basically the rank, the score, and then as the Guanaco here is the model that fully trained with the Q-Rolla technique, and then they achieve to better than GPT 3.5 Turbo, and we just train only one day budget, something like that. All right, so to summarize up everything here, as you know, if we fine tune the model, right, without any adapter technique of LoRa or Q-Rolla, you may need to you can think of the total area of the box here is the memory you require to train in the GPU to fine tune the model. So the base model, you have the base model transformer, whatever transformer you have, you store it into 16-bit. And yeah, you have to reserve some memory for the optimizer state as well, and then you update the model. But for the LoRa technique, you can just instead of you have big size of parameter you have to update, you can update just a smaller. And then for the Q-Rolla technique, the difference here is the original size of the model instead of 16-bit to the 4-bit. And then yeah, if you sum up the box here, yeah, this corner is the smallest memory required to train the model. Yeah, and that's all from me. Yeah, from DataX.
Yeah, and if you have any question, now would be the time. Yes, we have. Okay.
About the first part, I think it has to be some heuristic or some rule-based method to sampling or bootstrapping, right? If each of your samples has different type of distribution, it didn't indicate that compared to each other, different.
Yeah, that's right. Because what it did in the instruct mining, consider as the dataset level, doesn't consider about the kind of like the distribution in that dataset specifically. The point is we are gonna doing some research about the high quality dataset selection as well at the data point level instead. Yeah, that's the point of the kind of like the limitation of the instruct mining right now, as you mentioned, is correctly. Yeah, it's correct. Sorry. Yeah.
Thank you.
So, what methods are there can you use to like evaluate the quality of the data set?
The quality of the data set. If we would like to prove the claim of the instruct mining, maybe we can try fine-tuning it, full fine-tuning, or maybe use the technique that could have mentioned, LoRa, Crawler, whatever it is, to test that if we put different data set into the same pre-trained model, what will happen with the loss. Yeah, and hopefully it's gonna be kind of like consistent with what you found in the instruct mining.
Thank you.
All right, do we have any more questions? Okay.
When we see quantity doesn't matter, it's possible that it's because we always select similar data based on a single objective function. What if we also select some random data to our data set? Can we improve the quality? Like, let's say we select like top, let's say our data set consists of 80% of high quality data and then 20% of the, like, let's say lower quality of data. Can we improve the results?
Yeah, this one is a kind of like controversial right now because should we select only the best quality score into the data set that we can fine tune the model? Yeah, because there is a paper that called kind of like the Neptune something that try to introduce some noise into the weight, and it's basically makes the performance better somehow, which is unbelievable, right? Because we introduce some randomness into the model, and everything is better. It means that back to your question, if we have like cooking the data set by using only the cream of the data set, or maybe we can just put some bad data set into the data pool here, it may be improve the performance as well. You want to add something here? If you would like to add,
yeah,
just
so
interrupt me.
Maybe can go to the next. Okay, let me share a little bit here. So basically the idea of the instruct mining, it try to capture which characteristic of the data set that tend to when we fine tune the model, it get the lowest loss, right? And
yeah.
This one is proxy, so it basically can describe by this formula here.
Okay.
Like the reward score means that, okay, if your data set contain maybe more maybe this one, for example, here the understandability score. It means that if you want the data quality can I think it's have the correlation with the understandability score from those data sets, which contributes to
The highest impact, right? Okay.
So basically, if you want to get the low to optimize for your task, maybe you can consider the understandability to
Yeah, one thing that I would like to add here, everything here just doesn't matter so far. If we put the data set into cap like 50,000, everything stays the same, regardless of the quality of the data that you have. Yeah, but what we're talking right now is just if we have just small data set, can we enable or unleashing the power of small data set to this fine-tuning process? Yeah. So we can now focus on something less than 10,000 here.
Yeah.
All right. Thank you so much, Kapom. Thank you so much.
Thank you.
For the insight from the DataX team. So if you have any other questions, will you stay with us for how many days? For actually, you can book more mentor sessions if you want to.
Yeah, we have mentor session for DataX. So we have one for the track 1, which is me, and another one for the track 3.
So just let us know through the Discord that you want to talk to DataX team, so we can coordinate with that. All right. And then let's take a 15 minutes break before we have